Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 4.4 entitled Laws of Logarithms. And today we're going to talk about the laws of logarithms, and we're going to expand and combine logarithmic expressions and also learn the change of base formula, which is another way to evaluate logarithms. And when we're dealing with the laws of logarithms, this is basically the rules that let us combine log expressions together. So when you have two logarithmic expressions that are being added together, the way that you can combine them is to multiply what is actually being taken the log of. Okay, so you're multiplying the a and the b. And if you have subtraction, if you're subtracting two logarithmic expressions, whatever you're taking the log of, then you're going to divide those two quantities. And if you have a number out front of a logarithm, you can raise it up as an exponent on the quantity that you're taking the log of, and vice versa. You can also take the exponent and you can drop it down in front of the whole logarithm. And these expressions or these rules, they work forwards and backwards. So you can combine and then you can uncombine logarithmic expressions whenever you need to evaluate or solve an expression or an equation. Now, this proof that we're going to go through is just an exercise. I know you haven't seen proofs probably since geometry. As you get into higher levels of mathematics, you'll see more and more proofs. So I just wanted to show you that this property actually works. That if you have the log of, or log base a of a times b, it's actually the same thing as log base a of a plus log base a of b. So we're going to let log base a of a equal u. We're just going to set it equal to something. And then log base a of b, we're going to set that equal to v. And again, that's just a different something. It could be x or y. It could be p or l or m and n. It doesn't matter. We're just picking two random variables. So remember, when we start out proofs, we always start with our given. So that is our information that we have. And then I'm going to rewrite each of these expressions. So I'm going to do a to the u equals a, and then a to the v equals b. So those are my two expressions written here. So I just basically rewrote those expressions in exponential form. Okay, now they want me to prove that a times b is the same as a plus b, basically. So I'm going to take this expression log base a of a times b, and now that I know what a is and what b is, I'm going to substitute them in. So I'm going to put a to the u in for a and a to the v in for b so that I get this expression. So that's just substitution. Now we have to think back about our rules of exponents. Inside the parentheses here, I have two bases that are the same, and I'm multiplying them together. So remember, when that happens, you want to add your exponents. So really, I'm going to rewrite that underlined part as log base a of a to the u plus v. And that's just the rule that says when you multiply the bases, you add the exponents. Okay, that's just a good way to write our reason there for what we were doing. Okay, now if you think to our most recent rules with logarithms, when you have a base on the logarithm and a base on your power that are the same, remember that they cancel. So now I get u plus v that drops down. And all we did there was it canceled. And then up above, I defined what u was. U is log base a of a and v was log base a of b. So again, all I did was substitute, and now I've gotten to that statement that I was trying to prove. So I started with the a times b, and then I proved that it's equal to the a plus b. So my first two steps just basically helped me to redefine some of the expressions. So step 3 is where I really start to prove that a times b is the same as a plus b. So these properties that we're going to be using to expand and uh, compress, I guess, different logarithmic expressions really do work. Okay? And all we're going to do here for example 1 is we're going to use those laws and we're going to combine some of these expressions together. Here I have two logarithms. They have the same base. Now that's key. Logarithms have to have the same base if you're going to be combining them together. And right now they're being added. So to combine them together, I'm going to multiply. Okay, so you have to remember that addition and multiplication go together. So I'm going to rewrite this as log base 4 of 2 times 32. And 2 times 32 is 64. Okay, so that's now one expression that I have to evaluate. And these expressions we've evaluated in the previous sections of notes. So I would set this equal to something, and then I can do my little circle method to finish solving. So 4 to some power equals 64. And if you play around with your calculator, or you could um, try and figure out 4 to what power is 64, the answer that you get is 3. Okay, for part B, we're going to do the same thing. We have log base 2 of 80 minus log base 2 of 5. So again, the logarithms have the same base, and they're being subtracted. So to combine them together into one expression, I'm going to divide. Now when you divide and subtract, order matters, so you go in the order from left to right. So when I rewrite this, it'll be log base 2 of 80 divided by 5. And 80 divided by 5 is 16, so this is really log base 2 of 16. And now I have one logarithmic expression that I can evaluate. So set it equal to something, do the little circle method to rewrite it. 2 to the x equals 16. So you think, okay, 2 to what power is 16? Well, that's 4. Okay, now part C, I have a term out front of my logarithm, and I don't have a base written in here. So remember that that is going to be log base 10. So this is really negative 1/3 log base 10 of 8. Now when we have a term out front, remember we can use the property that says that that can be moved up as an exponent. So when I rewrite this, this will really be log base 10 of 8 to the negative 1/3 power. And when we're evaluating that expression, it's got a negative exponent. And you could think of it a couple ways. You could take the 8 to the negative 1/3 and put that into your graphing calculator and evaluate it. Or if it's a negative exponent, remember we want to take the same thing as 8 to the 1/3 and basically move it to the denominator. 8 to the 1/3, that's the same as the cubed root of 8, which is 2. So you can think through it that way or put it into your graphing calculator. But the 8 to the 1/3 is 2. This is 8 to the negative 1/3. So this is really going to be log base 10 of 1/2. So it's not just going to be 2. I didn't have 8 to the 1/3 is 2. I had 8 to the negative 1/3. So that 2 is going to move down to the denominator. So it'll be 1/2. Now the log of 1/2, if I was going to rewrite this with the little circle method, it would be 10 to some power equals 1/2. I don't know that. I can't evaluate that. So this one we have to do on our calculator. So you would just type in log of 0.5 and you will get negative 0.3010. Okay, so this one we do have to do on our calculator at the end to evaluate. And remember, when you're rounding values for logarithms, you want to round it to 4 decimal places at least. Okay, so now that we've taken a look at these properties, we're going to practice expanding and combining logarithm expressions. Okay, so this first one is expanding them. This is kind of like taking a compact expression and breaking it into its two separate parts. So here I've got the log base 2 of 6 times x. So that's multiplication that's going on between them. So remember, when you're trying to combine things together and you're using multiplication, that means you had two things added together originally that you were combining together with multiplication. So to uncombine them or expand them, you're going to undo that multiplication and turn it back into addition. So I'm going to have the log base 2 of 6 plus the log base 2 of x. And you go in the order that it was given here, with 6 times x. So you have the 6 first and then the x. And we can't really do too much more to this expression right now. All they wanted us to do was to expand the expression. They didn't say to simplify it or evaluate it or anything like that. So that's all we need to do for that one. We could evaluate log base 2 of 6. We could get a decimal for that. But the log base 2 of x, we can't get an expression or a value for that. So we just leave it as the x. Okay, for part B, there's really a couple different properties that are going on here. Okay, the x to the third and the y to the sixth, they are being multiplied. So we're going to expand them with addition. We're going to change that multiplication into addition. And then we also have the 3 and the 6 as exponents. So we're going to drop that down. I guess I'll just put exponent as a little note there. Okay, so this one's going to have 2 steps to it. So I'm going to break it apart first. Log base 5 of x to the third plus log base 5 of y to the sixth. So keep your bases the same, the log base 5 and the log base 5. And you just take your first term and your second term and you give them each their own logarithm and you break them up, spread them apart with addition. And then we're going to do our second step where this exponent is going to drop in front here and drop in front there. So we'll really have 3 times the log base 5 of x plus 6 times log base 5 of y. And then for part C, there's lots going on here. There's about 3 steps that we're going to do in this one. And the rules for expanding and combining logarithms work the same when it's log or when it's natural log. Remember, natural log is just log base e, so it's still a logarithm. Now I see division here. So normally when we have two logarithms that are subtracted, we combine them together with division. So if we're going to expand the division, that means that we're going to have to subtract. And then we're actually going to break apart this a times b. There's multiplication up there that we could break apart. So we'll break that apart with some addition. And then I also have this cubed root of c. And I could rewrite that as a fractional exponent and then drop that exponent down. So there's actually 3 steps we're going to be doing for this one. But first, let's start with our division, because that's the most obvious one there. So we take the numerator and then the denominator. We go in order. Okay, so I changed it from division to subtraction. Then this part here, that's multiplication, a times b. So I can break that apart into the natural log of a and the natural log of b. So break it apart with addition. And then this other part here, I'm going to rewrite that as the natural log of c to the 1/3. So instead of a cubed root, I'll raise it to the 1/3 power. And then I'll leave my natural log of a and my natural log of b. And then I'm going to take this exponent and I'm going to drop it down. So I'll have 1/3 times the natural log of c. So that's as expanded as that expression can get. So if you were able to see and identify all those areas where you can expand a logarithmic expression in part C, then you should be pretty confident with these concepts. Okay, now we're going to reverse the process and we're going to combine some of our logarithmic expressions together. And here it just says to combine it into a single logarithm, so it doesn't say to evaluate it, which is good because we've got some variables here. So I have 3 log x. Well, that 3 out in front, I can move him up as an exponent. And then I've got 1/2 log x plus 1. So again, this 1/2, I can move that up as an exponent. Now I have one logarithmic expression plus another logarithmic one. So that means eventually I could combine those two things that are being added together. I could combine them with multiplication. So let's start rewriting this. Let's rewrite our log x to the 3rd plus log of x plus 1 to the 1/2. So I've raised those terms that were out front, I've raised them up as exponents, but now I still have this addition, so I'm going to multiply. So I'll have log, and if you want to put the log base 10 in there, you can, but here's what we're going to be multiplying together. X to the 3rd times x plus 1 to the 1/2. And if you want to use 2 sizes of parentheses, you can. If you wanted to use brackets as the bigger parentheses, that's probably better, a little bit more official. But that's pretty much all we can do there to combine it together. Okay. And this is going to work with the natural logs too. Okay. Now, logarithmic functions get applied when we're dealing with all kinds of stuff, in particular human behavior. And here we have an example of how quickly you forget something. So if you take an algebra test and you score a 90% on it, so you're pretty proficient, and then if you don't use the algebra for a while, how long is it going to take you to start forgetting stuff? So how much will you remember after a week or month or year? And forgetting stuff is something that's a human problem that we try to not have. We try to always remember things. So Herman Ebbinghaus, that's a very big name, he studied this phenomenon and he came up with a law to describe this, this forgetting. It's called the law of forgetting. And he said that if a task is learned at a certain performance level, so p sub 0, then after a certain time interval, t, your new performance level, which is p, is going to fit into this equation. And notice there's logarithms. It says c is a constant, and it depends on the type of task, and then t is time measured in months. Now that's important there, measured in months. We might need that later on. Those are part A and a part B to this, and part A says that we want to solve that formula for p. So not p sub 0, we want to solve for this p right here. So how we're going to do that then is we're going to try to take out the logarithms. Okay, so I have on my right side of this equation, I have two logarithms that are being subtracted. So that means I can combine them together with division. So I'll still have my log of p equals, but now instead of having two separate logarithms, I'm going to combine them together. So I will have log, and then I'll have p sub 0 divided by t plus 1. Oh, and actually there was this c out in front, so I could raise him up as an exponent too. So I could have the t plus 1 to the c. So let me rewrite this just a little bit. Let's get rid of those parentheses there. And let's just do t plus 1 to the c. Let's do it like that. Now remember, these are log base 10s. If they're not written in there, that's a common log. And if you have a log set equal to a log, then you can cancel them out. So if I've solved for p now, it'll be equal to p sub 0 over t plus 1 to the c. So being able to combine my logarithmic expressions together on the right-hand side of this equation allowed me to eventually cancel out the logs and then really just have a nice algebraic equation here. Now for part B, we're going to use that equation and we're going to figure out that if you scored 90% on the history test, we want to figure out what's the expected grade that you can get after 2 months or after a year. And they also tell us what the constant is, which is important to know. So I'm going to write down our formula again that we had. We had p sub 0 over t plus 1 to the c. Now, if we want to find out what you're going to score in about 2 months, remember time was measured in months, so we'd want t to be 2. So we'll have p of, let's see, your original score was 90, and you had 2 months. Our constant is going to be 0.2. So if you evaluate the denominator, 2 plus 1 is 3 to the 0.2. We're going to get a decimal for that, 1.2457. And then when you divide 90 by that, you should get 72.25 or 72, let's say. So after 2 months, if you got an A on the test the first time, after 2 months, if you don't use that math stuff anymore, you end up with a C minus. And after 12 months, after a whole year, let's see, we would still have 90 over, now you have 12 plus 1 to the 0.2. So 12 plus 1 is 3, and 3 to the 0.2. Let's see, our p sub 0 is 90. That'll get you 13 to the 0.2, so 1.6703. And then when you divide there, you'll get 53.88. Or if you wanted to write it 54, if you wanted to write it, that's okay. So after about a year, you're going to be failing on that material that you learned once and were proficient at, and then you haven't learned it again. Okay, and we have one last concept then, aside from those applications of our logarithms, and that is the change of base formula. And the change of base formula is just another way that we can solve an algebraic, or I'm sorry, a logarithmic expression. I think it's a little faster sometimes, and here's how it works. Okay, if you have this logarithmic expression, log base b of x, and you're trying to evaluate it, up until now we've said, okay, set it equal to something, rewrite it so that it's an exponential form, and then what they're doing here for this proof is they're taking the logarithm of both sides, log base A and log base A. And then when you do that, this y will drop down in front. And then if you're trying to solve for y, because you're trying to find log bx, and log bx is equal to y. So here you're going to solve for y. So you're going to end up dividing log base a of x over log base a of b. Okay? And that's what the change of base formula looks like. Now it looks a lot more complicated than it really is. Okay? Usually you're going to have an expression like log base 2 of 3. And what you're going to do then is this log in the numerator and the denominator, they're bases. These are going to be our common logs. Okay, so I know it just says log base A, but we're going to use our common logs. And we're just going to take log of the bigger number over the log of the little base number. And then you can evaluate that. So this saves us from having to set it equal to x and then do little circle method. Because this problem, if I tried to do that, if I tried to set it equal to x and do my little circle method here, I'd have 8 to some power equals 5. I don't know what that is. Okay, so that's a very challenging problem to try and solve. So the change of base formula says that we get to do log base 10 of 5 over log base 10 of 8. So it's the log of your actual number over the log of your base. So think base goes on the bottom. So now in your calculator, just do log 5 divided by log 8. And you should get 0.7740. Watch your parentheses when you're putting that into your calculator. Depending on what kind of calculator you have, the logarithm might automatically open up a parenthesis for you. So make sure if that happens, you do log, and then with the open parenthesis, you type in 5, but then you close the parenthesis behind 5. And then for part B, you're just going to do log base 20 over log of 9. And that should get you 1.3634. And again, this just has you finding an answer in a different way than doing 9 to the x power equals 20. Because I don't know 9 to some power, I don't know that. I mean, 9 to the first is 9, and 9 to the second is 81. I got to get something that gets me 20. So I know it's got to be between 1 and 2, but to get that exact value, I'd have to do that work on my calculator. Okay? So practice that on your homework. This is really good homework for practicing those skills of expanding and compressing or combining logarithmic expressions and equations. And then there's a couple problems with the change of base formula as well to get you used to rewriting that and making sure you're putting the right number in the right spot. Okay, remember the base goes in the bottom. And remember the solutions are all worked out in the classroom in the binder. And if you have any questions, come see me before school.